Welcome, ladies and gentlemen. May I have your attention, please? Thanks. Let's go ahead and get going with our integration of integrand expressions where one part is not the derivative of the other part. So how do we undo a product in my integrand? Well, the answer is integration by parts. So we saw last class how we could choose u and dv such that the rewrite gave us u times v minus the integral of v du. We also want to make sure that we are comfortable with our prioritization, right? So we had that neat little acronym, LIATE, where we could assign priority by starting at the top. Logarithmic gets first billing, then inverse trig, algebraic, trigonometric, and exponential. So as you consider this first one, let's think about what would be most appropriate to choose for u. Okay, so let's go ahead and choose our u for number one. So what are we going to choose for u here? Sophia? X. Algebraic gets it.
Good job. That's close.
Awesome. So algebraic gets it, and then followed by trigonometric for dv. So we've got our x, and then we've got our cosine x dx. Please make sure that your selection for u dv fills up the entire integrand function, and it looks like everybody's covered. Now let's generate our other missing pieces. We need du, and we need v. So it looks like if u is x, then du is dx. If dv is cosine x dx, then v is the integral of cosine of x with respect to x. So that must be straight up sine x, no negatives. Hey! Things are looking up. Let's go ahead and perform our substitution then. We know that the integral of u dv is equivalent to u times v, so x sine x, minus the integral of v du. And so that's just sine of x dx. Hey, did our substitution into my integration by parts formula result in a simpler integral? Yes, and so now we can finish it out. No problem. This gives us x sine of x, and then the integral of sine of x would be opposite of cosine, but this was minus, right? This is minus, so it must be plus cosine of x, and then I always want to have a plus c. Awesome. Raise your hand if you had number one correct. Yes! Kind of a small, but you could count it, you know, particularly if you're down.
That's a big W.
Okay. I think number three might be a bigger W. Let's take a look at two, though, in the meantime. So, inverse sine of x, very different. Right, very different integrand here. So we want to choose this I for inverse trig. We're going to let u be the inverse sine of x, and then all that's left for the dv is the dx. So let's go ahead and continue with our selection here. U would equal inverse sine of x. dv would equal just the dx. And now we can go ahead and get our other pieces, du and v. All right, so if u is inverse sine of x, then du must be 1 over the square root of 1 minus x squared dx. So let's see if we can't get all that. So 1 over square root of 1 minus x squared dx. And v then would be given by the integral of dx, which is just x. I think we have it all. All right, let's go ahead and substitute in. The integral of u dv is given by u times v, so I'm getting x inverse sine of x minus the integral of v du. So that's x times 1 over square root of 1 minus x squared dx. Oh gosh. Too buku? I don't know. I think we're going to be just right here because I have two distinct pieces, two algebraic, right, expressions, but one now acts as the derivative of the other. So I don't have to have, right? I don't have to have integration by parts again. I can go straight with what? Power rule, where my quantity on the bottom is raised to the 1/2 power on bottom, or the negative 1/2 power off. Yes. So the good news is that the substitution into my integration by parts formula resulted in a simpler expression or integral that I recognize the rule for. So we can finish this bad boy out. I would need a 2 and a negative in order to have the derivative of the base. So I'm going to cancel that out with a negative and 1/2. right? And then we'd be good to go. So let's go ahead and go x inverse sine of x. And we needed, there's my derivative of the angle, add 1 to the exponent, divide by the new exponent, and I took care of the negative and 1/2, so plus 1/2. And this becomes 1 minus x squared. It was to the negative 1/2. Add 1 to the exponent becomes to the positive 1/2. Divide by the new exponent times 2. And then plus c. Let's see if we worked out the signs here correctly. So x inverse sine of x, like 2 times the 1/2 is plus 1. Radical 1 minus x squared. Close radical plus c. Raise your hand if you got that. Did anybody get the plus right there? Is that right? The plus? Hey, awesome work, you guys. That's awesome. All right, what questions do you guys have about number 1, number 2? So we've seen how up high on the totem pole for priority, right? We've got no problems. And then what happens when our expressions here, e to the x and cosine of x are both on the lower range, this liate, right? So we know now we might have more work to do because the derivatives as we go down, right, in my prioritization become more cyclical in nature. So we might have to do a couple u selections. So let's go ahead and consider which is going to get top billing here for our assignment. Vivian? E to the x. So when I choose my u, do I want to choose algebraic, trigonometric, or exponential first to be u?
Oh, sorry. So what do you think cosine?
Yeah, I'm going to go cosine of x just because that trigonometric is going to come higher than the e. And how do these prioritizations begin? Well, that e to the x is just going to continue over and over again. E to the x, e to the x, e to the x, right? Forever and ever. And the trigonometric is also cyclical, right? But it does change. And the idea is that we're hoping to generate another cosine here in 2 derivatives. So let's see. U equals cosine of x dx. Nope. U equals cosine of x. dv equals the e to the x dx. Now we're ready for our other parts. du and v. All right? So if u is cosine of x, then du must be opposite sine of x. Is that what you guys are getting? Opposite sine of x dx. And if dv is e to the x dx, then v must be just plain Jane e to the x. Now we're ready for our substitution. So it looks like we're trying to find the integral of e to the x cosine of x dx. And I know that's given by u times v. So that's going to be e to the x cosine of x minus the integral of v du, and that's plus e to the x sine of x dx. So it was minus the integral of v du, but then minus the negative is plus a positive. Are you guys okay? Great. So I did the substitution, and alas, my integral that we generated, right, minus the integral of v du, doesn't appear any simpler than the original. In fact, it's about on par with it, right? However, if we go again, the cosine went to the sine. We're hoping that the sine is going to go to the cosine again, and then I'll have multiple cosine expressions. And that's the goal here. But let's see what happens. So I'm going to go round 2. Let's go ahead and choose u and dv. This time, what are you going to choose for your u? Danny?
Cosine of x.
So this time, if we choose sine of x, and we choose dv to be e to the x dx, then we can go ahead and generate our other pieces. Gosh, I hope this works out. It'd be pretty sweet. It'd be pretty sweet if it did, huh? So I'd take the derivative of sine of x, go to cosine x dx. Ah, that's looking familiar, right? Cosine x dx. And if I go from dv as e to the x dx and step up the latter one rung, I'm going to get, again, e to the x. So we'll keep the entire party here. We had integral of e to the x cosine of x dx equals e to the x cosine of x plus, and now we're going to go ahead and do our second substitution. So here's our second substitution, round 2 for u dv. I know the integral of u dv is given by u times v, so that's e to the x sine of x minus the integral of v du, minus the integral of v du. So v is e to the x du is cosine of x dx. And when we first saw this, it appeared as though we were getting absolutely nowhere, right? We wanted to know what e to the x cosine of x dx was, and here we generated yet another e to the x cosine of x. And so that's bad news bears. Except that that's my unknown, right? I'm looking to figure out what the integral of e to the x cosine of x is. And so if I were to think of this as my unknown and add over to combine like terms, I could solve for that unknown and get the answer. So that's pretty darn cool. I'm going to go ahead and add this integral to both sides and generate two unknown integral of e to the x cosine of x dx. And that's given by e to the x cosine of x plus e to the x sine of x. And now we can simply divide by 2, add a constant integration, and we're good to go. That is really cool. I like that technique. And so we can divide both sides to undo that multiplication, and we're done. We found our unknown. The integral of e to the x cosine of x with respect to x is given by 1/2 e to the x cosine of x plus 1/2 e to the x sine of x plus c. And I've seen this all over too, but I've also seen the 1/2 as a coefficient out front, like in tables and stuff like that. And so either one is fine. Raise your hand if you got all the way to the end of number 3. Did anybody get to that? Isn't that a cool technique? You regenerate your unknown expression and solve for it. I think it's pretty cool. But then again, I'm a math teacher. I'm excited about that kind of thing. Awesome. What questions do you guys have about today's Bellwork? Count it as a W? Monday's looking up? All right. Let's go ahead and pause the recording and take care of our OTL check then, please. Okay, ladies and gentlemen, so we just saw 3 times, right, how great this integration by parts formula is. Again, it undoes the product rule. When we have a product in our integrand where one part's not the derivative of the other, we can tackle that. We had our priority, right, our prioritization for assigning you Liate that was from my AP Calculus BC teacher a long time ago when I was a student, like before they had television and stuff like that. And now we're going to go ahead and switch gears. I want you to go ahead and use these kind of as a warm-up. So what we're going to do is we're going to sort of tackle these problems to see both where we've been and then give us a lens into where we're headed. Okay, so we've got a brand new technique on the horizon. The cat's out of the bag because it's on your note sheet and in the agenda. We're going to integrate using partial fractions, which is a brand new technique. But first, let's see how we get there. So, are we able to integrate number 1 as is? Well, certainly. We have that derivative, right, of the quantity on the bottom, all to the first. It's just 1x, and so the derivative is just 1 dx. I can treat this as quantity on the bottom to the first power, which makes it a candidate for, Sydney?
Natural log.
Natural log, and so it looks to me like I could simply move this 4 out front so I don't trip on it as a constant multiplier. The derivative of the base is present. So I can go straight to natural log of absolute value of x plus 9, close bars, plus c. Nothing new there. Right? In fact, that's so 2008. Let's take a look then at number 2. Are we able to integrate number 2? Well, it's been a while, right? It's been a while. Though we did tackle these types of problems in AB, right, towards the very end of the year when we looked at additional integration techniques. And so first thing is, I want to free ourselves from distractions. So what I'm going to do is I'm going to rewrite this thing, perhaps unnecessarily for you, but I'm going to just go ahead and move that 5 out front so that I don't worry about it. And I'm going to put x over x plus 9. Right now, the degree of the numerator and denominator are the same. They're both x to the first. And so clearly, this x can't act as the derivative of this function on the bottom, right? Moving towards a natural log or a power rule or something like that. They're the same degree. And so upon initial inspection, it seems like I have too much x. We handled this in one of 2 different ways. The first was kind of the clever algebraic trick, right? In that we added a clever 0. I can make this x plus 9 minus 9, and then group the x plus 9 over x plus 9 and split up the fraction, and then minus 9 over x plus 9, and then I'd have I'd have a sum or difference in the numerator, and I'd just have a constant function and a natural log function. However, we can set this up so that it's in more general, right? So we don't have to memorize a special clever little trick. If the degree of the numerator is greater than or equal to the degree of the denominator, we can handle this with polynomial long division. So that was a technique that we looked at last year. I could simply take the top x and divide it by x plus 9 to rewrite in rational form. So let's go ahead and focus on our dominant term. X goes into x one whole time. Then I multiply top times the side all the way through. 1 times x plus 9 all the way through is x plus 9. And then our long division algorithm says, what next?
Oh, no.
No? Are you with me? Subtract? Thanks. Thanks. You guys didn't skip this. Did you skip this?
Yeah.
You skipped the long division algorithm for numbers and went right to it with polynomials?
Yeah.
So, hang on. So we're going to resume with this, right, in just a minute. But right now, we're going to do our, that's not 11, that's pause it. So we're investigating, right? We're investigating x over x plus 9, right? And we're going to do it by pretending that those numbers 40 divided by 3, right? So what do? Well, I go ahead and say this would be 40 divided by 3. And I say, okay, so 3 goes into 4 how many times? 1. 1 times 3 is 3. Yes?
1.
And
Drop the
then
0. That's 3. So we got the remainder.
and subtract, and then 4 minus 3 is 1, and then bring down, and then 3 goes into 10 how many times?
3.
3 times, and then top times the side all the way through. 3 times 3 is 9, and then subtract and 1, and so it looks like 3 goes into 40 13 times with 1 left over. So you guys seeing that? So we're 13, remainder 1. Yes?
Yeah.
Okay? Okay, now, let's pretend that we're not doing that, and then we're doing x divided by x plus 9. Let's do the same thing, but let's focus on the algebraic expression. Dominant x goes into x how many times? 1 whole time. Top times the side, all the way through. That was my top times the side, all the way through. There's my 3. Ready? So top times the side, all the way through is x plus 9. Then what do? Subtract. So we subtract, and I get x minus x is 0. And we remove our pause. That's on 11. That's pause. Play. And I get minus 9 as my remainder. How do I know it's remainder? Because x doesn't fit into 9, right? And so now I've got 1 remainder 9. So x plus 9 goes into x 1 whole time with a remainder of 9.
Negative 9 or 9?
Negative 9, thanks. Thanks, full time. All right, so let's just, so the only reason we did polynomial long division was so I could rewrite this rational expression, hopefully, as an integrand that I recognize rules for. Let's do that. So I've still got my 5 out front, yes? Times the integral of, so what are we doing? Well, we're rewriting x over x plus 9 as 1 minus 9x plus 9. And we're going to see if that's helpful. In the same way that this is 13 and 1/3, right? 40 thirds is 13 and 1/3. In the same way that x plus 9 is 1 and negative 9x plus 9. So I'm saying that the side thing is your denominator of the remainder. Yes.
Never mind, I think.
Let's do it.
Okay.
Was the polynomial long division useful?
Yes.
Did it result in an integrand for which I know rules?
Yep.
Yes. So now I can go term by term. So this is 5 times antiderivative for 1 is x antiderivative for 9 over x plus 9 is now just like the first one, isn't it? Minus 9 ln of absolute value x plus 9 close bars plus c. And I've got my 5 out front, and so I only did that so that I wouldn't trip on it. I could have left it there the whole time. I could have included it in my polynomial long division. I just moved it so that it was one less thing to worry about. Now I'll distribute it back through. Awesome. Okay, so while the second one was a little bit uphill, we're still 2 for 2. I mean, all things considered, we're still 2 for 2. Let's check out number 3. Do we possess techniques, right, to integrate number 3? Well, in terms of having multiple algebraic expressions in my integrand, we're always looking to see if one is part of the derivative of the other. And while these degrees differ by 1, that is to say that x to the first is 1 whole exponent away from 2, this quantity cannot be acting as part of the derivative of the x squared because, 1, it's in the denominator, right? So it's really on the bottom of a fraction with exponent -1. It's also a quantity. And so this is not a chain rule problem. And yet, we just reviewed a technique where you can practice right now. If the degree of the numerator in my rational expression is greater than or equal to the degree of the denominator, like this, then we can try what to rewrite? Yes, we can try polynomial long division, which is what you're going to do right now to try and remind yourself, because it looks like we need a little reminder. All right. So as you're trying, I'm going to do it at the same time so you can be checking, but I'm not going to talk right now just for a minute to give you guys a chance to try.
Me too. Sorry. Me too. I don't think you. I got to the 9x.
Are you wrong?
I doubt it. No. I'm just a little confused. I'm stuck at green now.
So we're back. That's why the color coding there, so we can focus right in on where we are, where we aren't. So ready? I did x squared divided by x plus 9, and I focused on the dominant. X goes into x squared how many times? X times, right? Because x times x is x squared. Then I do top times side, all the way through in blue. Ready? X times x plus 9 all the way through is x squared plus 9x. Next, subtract. So I subtract quantity. When I subtract this, I know I'm doing it right if these cancel out. So the x squared minus x squared was 0. Good. Minus 9x. Now I try again. X goes into minus 9x how many times? Negative 9, because negative 9 times x is negative 9x. Ready? Top times the side, all the way through in black. Negative 9 times x plus 9 is negative 9x minus 81. Yes? What's next? Subtract. So I'll go straight down. Negative 9x minus a negative 9x, right? This should give me 0 x's if I'm doing it right. And then minus a negative 81 is 81. I know that I'm done, right, when my dominant no longer fits into, right? I can't say x goes into 81 how many times, so that's my remainder, which means I can now rewrite my original rational expression as...
Oh, no.
Oh, did you guys see that? No problem. No problem. Everything's good. So we can now rewrite our original as x minus 9 plus 81x plus 9. Let's see what it looks like.
But you really don't have to. Oh, you are on the same page.
Big writer. Was that helpful? Yes, because now we can go term by term and we have a rule for every single term in my integrand expression. Yes? Okay, so we'll go ahead and go term by term. The integral of x with respect to x is x squared over 2 minus 9x. And then what rule would I have for the last now? Natural log again. So plus ln of, well, I'm going to do 81, sorry, 81 in front. So plus 81 ln of absolute value x plus 9, close bars plus c. Yes? Okay? And now, we're going to move that right back up. No problem, no problem. Just a touch. We want PDFable, baby. Don't we strive for PDFable? Okay. 1, 2, 3, counting it. Up to 4. Do we currently have techniques that would allow us to integrate number 4?
Yes.
Yeah, you guys just did 2 class periods ago. Do we recognize an x squared on bottom, right? An x squared on bottom, and no x's on top, right? With a sum, right, could be rewritten as what? Inverse tangent, right? We're trying to make this look like inverse tangent. If we can make it, but inverse tangent has 1 plus input squared built into its rule. And this is 9 plus, and so it's not ready for inverse tangent, but I can certainly factor, right, to rewrite that as 1 plus input squared, as we did last class. And so again, I'll pull the 6 out. Do a little factoring. So for factoring, I'm going to go ahead and make this 9 times 1 plus x squared over 9. Do a quick check mentally and make sure that produces my original denominator. 9 times 1 is 9, plus 9 times x squared over 9 is x squared. My original was 9 plus x squared. So I factored out a 9 in such a way that I'm trying to make my denominator look like 1 plus argument squared. Meanwhile, right, I'm going to pull this 9 out with the 6 to make this a little bit prettier. That would be 6/9 out front, which will reduce to 2/3. But I don't want to do too many steps all at one time. And rewriting my denominator as 1 plus argument squared sets me all up for inverse tangent. What quantity squared equals x squared over 9?
3. Oh, shoot.
X over 3,
My bad.
baby. And x over 3 would be a derivative, right? A derivative of 1/3 that I need in order to go to inverse tangent. And I'm going to go ahead and put that 1/3 here. There's my derivative of the argument, and I'm going to cancel it out with a times 3 on top. So I've got lots of constants floating around, but we can handle that, right? There's nothing new there. I've got 2/3 times 3 over 1 is simply 2, right? Are we just getting 2 there? Now I'm ready for inverse tangent of angle was, I'm sorry, input was x over 3, close, and then plus c. Okay? So this is supposed to be kind of recap, refresh where we've been, and see where we're going. Sydney.
Can I just have you go back just like 2 steps to
Yep.
that 1/3 up on top?
Yep.
Why is that up there?
So I was informally, right, thinking about what I would need in order to go to inverse tangent for an antiderivative rule. In order to do that, I need to know my chain rule, right? I'm trying to undo the chain rule. The derivative of inverse tangent is 1 over 1 plus input squared times the derivative of the input.
Since that
If
was
I
there,
had a 1/3
okay.
there, I could go to inverse tangent, but I didn't.
Yeah.
So I need to account for that by providing a. You tell me.
The 3 of them from
Yes.
Yeah, yeah.
Now I can go inverse tangent because I have the derivative of the input, right?
Gotcha. Thanks.
You're welcome. You guys okay? Are we okay?
Good one.
Gosh, feels like it should be Tuesday already after those first 4. And we're not even there yet. All right. So what's up? Oh, goodness gracious. What? Here we are. Stay strong. All right. So as I'm looking at number 5, right? So far we're building. We're thinking, do we have a technique that will handle number 5?
We do.
What? We do?
I think so. We can like break it up into factors and then.
We could rewrite the denominator, right? So if we're to rewrite this denominator, and pull the 7 out.
Oh my gosh.
If we're to rewrite the denominator, how would that help me? Well, x squared minus 6x plus 9, right? Isn't that a special?
Yep.
What is that? X
X
minus 3 squared. And how does rewriting it like this, right, make it easier to see a rule? Because the derivative of my base in this power rule is just 1. And I've got it. I can go straight to power rule. My denominator, right, is raised to the 2. Overall, this is simply a power rule whose current exponent, bless you, is negative 2, right? Awesome. Let's do it. This isn't bad. So I just get 7. I don't have to provide a constant. X minus 3 to the, add 1 to the exponent and divide by the new exponent. Right?
Yep.
So quick rewrite. Equals negative 7 over x minus 3 plus c. Is that right? Yeah! Okay. Pretty cool. All right. So it was my hopes in these first 5 that would be like, yeah, we already have a lot of tools in our bag, so to speak. Sydney.
I'm sorry. So
It's okay.
I wanted to distribute that 7. Can you not do that?
Where?
Like in the blue there?
Right here?
Yeah.
No.
Oh.
The 7 does not have an exponent of negative 1. If you wrote it as 1/7 the negative 1, then you could, in accordance with the power rule
Okay,
for
so just don't do that.
No.
Okay.
It's not part of the it's not in part of the parentheses. Exponents take priority over multiplication is the short answer to that.
Okay.
See that negative 1?
Yeah.
Okay. All right. Are we good? Are we good? Okay. Do we have a technique to handle number 6?
Probably.
Well, where we could rewrite the denominator in number 5 in such a way that I recognize the rule, right? Could we try rewriting the denominator in such a way where we recognize the rule?
Yeah. Maybe. Yes.
Yes? Okay. So how do we write it better? Well, is it special?
No.
No, it's not special. But we can still rewrite it as, I'm actually going to make that 1 in anticipation. So what would the denominator be rewritten as? Well, what do you want to do? Factor it?
Yeah.
So we make it as
Minus 1 and plus minus 9.
x minus
Nine.
1 and x minus 9.
Yep.
Then x squared minus 9x minus 1x is minus 10x and negative 2 times negative is positive 9. Yes, this is fully factored form. Does that help me? No, right? It doesn't help me unless we're able to rewrite this rational expression, right, using a technique known as partial fractions, that is, as a sum or difference of individual simpler fractions. And I want you to think common denominator. So right here is where, can we do the little pause button again?
Yep.
So here's my little pause button again.
What does it stop?
It's not 11.
No, it's not stop.
It's not 11. It's a pause.
Quick break.
Bless you.
Bless you.
After this warm-up, you're going to be reminded of how we handle a common denominator and get that 2, right, that product of linear factors in the denominator. That's going to allow us to go backwards and now handle number 6. So here we go. Our warm-up today is to write this rational expression in standard form. Okay, so we're going to rewrite this in standard form. So we need to create a common denominator because we have a sum or difference of individual fractions. What would that look like? Well, I consider the current denominators. I've got x minus 2, I've got x plus 1. So the first one, right, in order to create a common denominator, the first fraction needs an x plus 1. So I'll multiply that first fraction by x plus 1 over x plus 1. So this first one needs an x plus 1 over x plus 1. Yes? And what does the second fraction need in order to create a common denominator so I can combine these two? Well, it needs an x minus 2 over x minus 2. Again, we're just multiplying by 1 in green, so we're not changing the value of the original. But in doing so, we create a common denominator. I now have 3 times x plus 1 over quantity x plus 1 times x minus 2 minus 2 times quantity x minus 2 all over x plus 1 times x minus 2. And we're not going to do this in as excruciating detail every single time, but I want to make it clear where this comes from and what we'll be using. So now I have a common denominator. So my rule is after making a common denominator, I can combine the numerators through addition or subtraction and rewrite it as a single fraction all over the common denominator that we strove to create. Let's do it. 3x plus 3 minus 2x plus 4 all over x plus 1 times x minus 2. Which means that I get on top 3x minus 2x is x, and plus 3 plus 4 is plus 7.
Yeah.
All over x squared minus 2x plus 1x minus 1x minus 2. Got it? Standard form rational expression, polynomial we're used to seeing, yes? So now we're going to turn the tables. We started with polynomial standard form rational expression, right? What we're going to do is decompose this into a sum or difference of individual simpler fractions, again with the goal of creating an integrand for which we have antiderivative rules, okay? So we first need to get it in fully factored form. We saw how that fully factored form was what generated my original, so we're going to now consider what if the original had been the integral of x plus 7 over x squared minus x minus 2. What are you asking?
I don't know.
So what if we were charged with the task of integrating quantity x plus 7 over quantity x squared minus x minus 2? Could we do it, Sophia?
Rewrite it.
Absolutely. Notice how this original, right, this expression is equivalent to that. So our goal today is to take a rational expression in standard form, right, and rewrite it as a sum or difference of simpler fractions so that we have rules for them and can integrate term by term, just as we did in our warm-up 1 through 5. So now we are well equipped. We see the direction that we're headed, right? That's where we're headed. So how would I do it? Well, what's my original? It would be rewritten as, what was it? 3 over x minus 2. Minus 2 over x plus 1. And then dot, dot, dot. So we know how to do that. Now we have 3 natural log of x minus 2 minus 2 natural log of x plus 1 plus c. And I have to tell you that the back of your textbook, right, we'll go a step further and combine these into a single logarithm using the logarithmic properties. They'll kick up this 3 on top as an exponent. They'll kick up the 2 on top as an exponent, and they'll rewrite a difference of logs as a quotient. And so I just want you to know when you're checking your answers in the OTL, as I strove to choose odd exercises, right, you'll see this as ln of x minus 2 over x plus 1 squared. And then you also be like, well, how come the bars disappeared? Then you'll be like, oh, because it was squared and blah, blah, blah. But I just want you to know that this in black is totally fine, but when you're checking your answers, you'll see that, right? You'll see that in the back. Would it make you feel better if I box this?
Yeah.
Yeah.
So you kick the 3 up on top, you kick the 2 up on top, and then difference of individual logs, the log quotient. All right, ready? So let's see if we can tackle this. All right, so our job now is to rewrite that integrand, that rational expression, x plus 5 over x squared plus x minus 2, right, as a sum or difference of individual, right, simpler rational fractions for which we know the rule. This is only going to be possible if we can rewrite in fully factored form as a product of distinct linear factors here for us. Okay, so we have to make that denominator in fully factored form in order to be able to see if we can do this. So first things is I'm going to go ahead and focus on this in fully factored form. I think I'm going to do a big bracket and start our process here. So we're going to take our original x plus 5. This does not equal this. We're just focusing on the integrand there. Over x squared plus x minus 2. And we're going to rewrite in fully factored form. So I've got x plus 5. What would that denominator become?
X minus 1 and x plus 2.
You guys down with Sydney's factorization? Is that good? So we're fully factored form. We're a product of linear factors. So this is heartening because that's exactly, right, what we had before, albeit with different numbers, but we had something like that before. So our job is to figure out, right, simpler fractions that sum to give me this. And our technique for doing it is going to be called partial fractions. So what we're going to do is we know that this, right, this comes from some numerator over the x minus 1, right? Some numerator over the x minus 1 plus some numerator, which I don't know, right? Some numerator over the other linear factor, x plus 2. And we know that that's going to be equivalent to that x plus 5 over x minus 1 times x plus 2. Turns out that we can always do this, right? If we can write that in fully factored form, it turns out that we can always do this. We can always find values of a and b that'll make this true if we can write that in fully factored form as a product of factors. All right, so what are we going to do? Well, what did we do in order to rewrite a sum or difference of individual fractions as a single fraction? Right? We made a common denominator, which is exactly what we're going to do here. So our effect hinges on taking that a times the x plus 2 plus the b times the x minus 1, and that's going to give me the x plus 5 numerator. Right? That's where this comes from. Yes, we could write it over as quantity x minus 1 times x plus 2, but it's unnecessary because we're just trying to figure out what a and b are, and we're already using those denominators as my multiplier. So let's go ahead and see what happens. Ready? A times quantity x plus 2 plus b times quantity x minus 1. This has to equal what? It has to equal x plus 5. When I combine those, right, I have to get that x plus 5. All right, can we figure out what a and b are? Yes, and we can do it a couple different ways. We could distribute through combine like terms and then equate coefficients. That is, see what the x terms would have to be, all right, in order to equal this 1x, and see what the constants would have to be equal to 5. But I think an easier, quicker way is to purposefully choose values of x that make the one constant drop off and allow me to solve for the other. In other words, if I chose x to be -2, it would result in a 0 times a, which would make that drop out, and I could just solve for b. Then I can go back and choose x to equal 1 purposely, because then 1 minus 1 is 0. The b term would drop off, and I'd be able to solve for a, which is what I want. I want to know what a and b are so I can rewrite my original, right, and integrate term by term. So I'm going to let x equal -2. And when I do so, I get the a term dropping out, and I get -2 in for x. -1 is -3b. Does everybody see that? We're letting x equal -2, so the a term drops out. And I'm letting x equal -2, so the right-hand side becomes -2 plus 5 is 3, which means that what must be equal? -1. Alternatively, let's let x equal, what else should I choose x to be? 1. If I choose 1 for x, then the b term drops out, and I'm left with 1 plus 2 is 3, times a is 3a, equals, and I chose x to be 1, so the right-hand side becomes 1 plus 5 is 6, which means that, what does a equal? 2. All so that I see my original x plus 5 over x squared plus x minus 2 is equivalent to what? 2 over x minus 1 minus 1 over x plus 2. If I rewrite my original like that, then it will be easy to integrate. So we've got one more step. In fact, it's going to be a quick one. My original x plus 5 over x squared is equal to 2 over x minus 1 minus 1 over x plus 2. So these are equivalent, right? These are equivalent. I better not put that. So why was that helpful? Well, because now we have a rule for 2 over x minus 1 minus 1 over x plus 2. I get 2 natural log of absolute value of x minus 1 minus ln of absolute value x plus 2, close bars, plus c. That's pretty sweet. Let's try another. All right, let's try another so we can see how this scheme works. So we're going to rewrite the rational expression as a sum of simpler fractions, and here's all the space that I made so that I didn't have to cram it in last slide. Let's try another. Still there. All right, so here we go. I'm going to rewrite. All right, I'm going to rewrite that 1 over x squared minus 5x plus 6 as a sum or difference of simpler fractions. In order to do that, I need a fully factored form. So let's go ahead and see what that's going to look like. 1 over, and this time, right, this time, what's my denominator going to factor to? Grace?
X minus 3 times x minus 2.
X minus 3 times x minus 2. You guys good? All right, I know that this has to equal a sum or difference of simpler fractions, each with the same, right, with one of those factors in the denominator. So I'll go ahead and arbitrarily choose a over x minus 3 plus b over x minus 2. All right, so I know that a over x plus 3 plus b over x minus 2 equals the original. How would I see what a and b are? Well, I need to make a common denominator in order to combine these fractions and set equal to the top. So what does this a need? A needs the x minus 2. So a times x minus 2 is equal to, no, plus b times, I want to be on that side. Here I am over with this wrong side equal to b times x minus 3, right? And I know that that's going to equal 1. So this is what I'm going to do. I'm just changing my sides here.
Are we still in the bracket?
Yep. All I did was switch my order because I want to take ax minus 2 plus bx minus 3 and set equal to 1. Because I know when I multiply a times that x minus 2 and b times that x minus 3, they have to combine and give me the 1 on top, all over my common denominator that we just created. So what would be good values of x to choose? 3. Right, let's let x equal 3. So let's go ahead and say let x equal 3. When I let x equal 3, I get 3 minus 2 is 1 times a is a. plus the b term's gone because we chose x to be 3 on purpose, equals 1. Can we see what a equals? A equals 1. What would be another good value to choose for x? 2, let's let x equal 2. When x equals 2, then the a term disappears, and I'm left with 2 minus 3 is negative 1 times b is negative b, and that equals 1, which means that b equals what? So b equals negative 1. So my original 1 over, now we're close brackets in. So my original integral of 1 over x squared minus 5x plus 6 is equal to the integral of a is 1 over x minus 3. B is negative 1 minus 1 over x minus 2. Close brackets, dx. Was this helpful? Yes. Now we have term by term, simpler fractions, and we can go what, ln again? Oh my gosh. That's pretty sweet. Cool. All right. You guys ready to try one with your partner, or do you want to still do it one together? So you're gonna go ahead and try one with your partner. I'm gonna pause the recording. You're gonna try with your partner. You can talk it.
We have like 5 things.
Okay. So we've gone ahead and we've rewritten in fully factored form, right? Our fully factored form will allow us to rewrite as a sum or difference of individual fractions. We've figured out the values of a and b. And now we're ready to integrate term by term. So again, I'm getting a natural log 2, natural log of absolute value x minus 3 minus natural log of absolute value x minus 1, close bar plus c. Raise your hand if you and your partner got the same thing. So who else already got that? You guys get there? Yes? Then you've got the basis for partial fractions. Good job. So then what do we need to be on the lookout for? Well, we have to be on the lookout for when my numerator, right, when my numerator has a degree that's greater than or equal to my denominator. So the technique of partial fraction relies on rewriting in simplest form, right, so that I can do fully factored form. That one we can hold off on because it's the same deal, but this one has an added layer. So what do we have to do first? Well, in order to rewrite this as a sum or difference of individual fractions, we have to first go ahead and do, right, our polynomial long division. So yes, if the degree of the numerator is greater than or equal to the degree of the denominator, then we want to do polynomial long division. So this is a great opportunity to practice because this one's tricky, yes? Let's go ahead and first rewrite. So I didn't leave space, and sometimes, right, people leave space for the x squared term to keep things when they bring down. It's fine for you to do that too, but I know that I'm going to be condensing when I get down to the bottom anyhow. So you're welcome to leave space and make it plus 0x squared minus x plus 3 and make it 4 terms if you want. Just keep it in standard form. That's totally fine. I'm not going to. I'm going to focus on my dominant. Dominant goes into dominant how many times? X times. Tops times the side all the way through. Next, subtract. So x cubed minus x cubed is 0x cubed. That means I'm doing it right. I have 0x squared minus x squared is negative x squared. Stick with me here. We've got minus x plus 2x is plus 1x. And we still have the 3 bring down. So this was a positive and it's a bring down. It's not part of the subtraction.
Oh.
This is another step. So there's the subtraction and then we bring down. Yes, in my algorithm?
Yep.
You guys okay? Dominant. X squared goes into negative x squared how many times? Negative 1 time. Top times the side all the way through. Let's do it. Negative 1 times, and let's go all the way through. Negative x squared, I'm sorry. Yep, negative x squared minus x plus 2. Everybody see that? Is that right?
Yeah.
Next step, subtract all the way through. Negative x squared plus the positive x squared is 0x squared. That's what we wanted. X plus x is 2x. 3 minus 2 is 1. I know that I'm done because the dominant x squared doesn't fit into the dominant here anymore. So what's my remainder? My remainder is 2x plus 1. Well, let's hope that this was helpful, right? Let's hope that this was helpful. So I'm going to go ahead and rewrite my original. I know that, yes, Grace.
So in the black,
Yes.
there's one in the black. Why is it plus x and not minus x?
Great. So it might be. Let's see. So are we 2 right here? So we said x squared goes into negative x. No. Right here.
Yeah.
So first step, which can mess everything up if this is wrong. So let's see. X cubed. X, so x all the way through. So x cubed plus x squared minus 2x, and now we're subtracting. So subtract. So minus an x squared is minus x squared.
Okay.
Yeah. Okay. Cool. Let's go ahead and rewrite my original and see if it was helpful. Here we go. The integral of my original rational expression is equivalent to x minus 1 with the remainder of 2x plus 1. So plus the integral of 2x plus 1 x squared plus x minus 2. Don't do this. That's my remainder. Okay, my single integral sign. There. So, did everybody see that? We rewrote that as x minus 1 plus 2x plus 1 over x squared plus x minus 2. Closer? No. Yes?
Yeah.
Okay.
I bet.
So now, right, we generated a situation where my numerator in the rational expression is less than my denominator. So now I can use the techniques that we already have, right? One of them is now, I'm including partial fractions as one of those techniques now because we've done that a couple times today. However, there's a couple ways to do this. We don't have to do partial fractions if you're good with chain rule, right? What do you recognize about the denominator and the numerator here? Yeah, and isn't it straight up? I don't even have to do a constant. What if I can interpret this quantity on bottom as yes, it's a composite function, right? Where my input is x squared plus x minus 2, but isn't that all to the first power? And what's the derivative of that function? No, I mean, what's the derivative of x squared plus x minus 2?
2x plus 1.
Which is
right up there.
right up there. And so we could do partial fractions for this. We could.
No.
But if you recognize that, and I'm trying to mix everything up, you know what I'm saying? So we've got lots of, so in our build-up, I was trying to say, oh, look at all the tools we have. Oh, here. So if you recognize that this 2x plus 1 is the derivative of the base, you don't have to continue on. You can go right to your natural log rule and turn my trick. So I'm going to do that. Because, hey, we're all about saving time, baby. Efficiency.
Taking the W.
I screwed it. Minus x. Plus, that's it. Natural log?
No.
Uh-oh. Where am I going to put my plus c's in?
Mine's on page 2, so.
Right here. Don't need anything else. That's it. We win. Nice work.
Okay.
That was pretty sweet. Gosh, I feel like we got a lot in our bag.
A lot of W's today.
All right. So what's tricky? Well, gosh, this looks like the last one, but is the degree of the numerator greater than or equal to the degree of the denominator?
No.
No. Is the numerator the derivative of the
Not
denominator?
quite.
No. Well, let's go ahead and see if we can do partial fractions. In order to do that, we need to first rewrite in fully factored form. So let's go ahead and see if we can rewrite this in fully factored form.
See it on the bottom? See what I'm saying?
Oh, yes, but is it going to cancel anything on the top?
I don't
Oh,
know.
we don't want to cancel.
No. Okay.
Well, we want to factor. Yes, do you see it on the bottom?
Yeah, that's what I'm saying.
What? Is it x?
X.
A lot of fractions.
I don't know. It's not good. Do you see what I'm saying?
Can we keep going?
Yeah.
So now what is the I'm going to factor in 2? Everybody found it?
2x plus 1.
What's the end?
2x plus 1 times x minus 2. So let's do a quick check. 2x squared minus 4x plus 1x would be minus 3x.
Uh-oh.
One little shift in painting will make that work. So 2x minus 1 and x plus 2.
Yeah.
Let's try
There we
that.
go.
Plus 4x minus 1x is plus 3x minus 2. Good job. All right. So if we write in fully factored form, I know that I can decompose this. For sure. Guaranteed I can rewrite this as the sum of difference of individual fractions with denominators, right, of x, 2x minus 1, and x plus 2. Let's do it. So I'm going to go ahead and set up my fractions. I know that a over x plus b over 2x minus 2, 2x minus 1 rather, plus c over a third fraction, yep. I know that this has to equal x squared plus 2x minus 1 all over x times 2x minus 1 times x plus 2. So now what do? We make our common denominator. Yep. Doing perfect. Ready? Here we go. What does the first fraction need? It needs 2x plus minus 1 and x plus 2, right? That's what the first fraction needs. So a times 2x minus 1 times x plus 2. What does the second fraction need? The second fraction needs x and
X plus 2.
x plus 2. What does the third fraction need? X and 2x minus 1?
Yeah.
And all together, I know this is going to equal. Sorry, Drew.
Yeah.
All together, I know this is going to equal what? What does this have to equal? X squared minus plus 2x minus 1.
Yeah.
Let's do it. All right. What are some purposeful selections of x that will help us?
2.
Let's let x equal 0. I'm down.
Ah.
If I let x equal 0, look at that. Be gone. Be gone. C's gone. X is 0, so I get negative times negative 1 times 2 is negative 2. A equals 0, 0, negative 1, which means that A equals what? No, positive 1 half. Oh, no problem. Let's let x equal, Grace, you're going to say negative 2?
2.
2?
Nope, -2.
Negative 2.
Oh, man.
When x equals -2, the first term disappears, the second term disappears, and I'm left with c times -2 times -5 is positive 10 equals -2 is 4 minus 4 is 0 minus 1 is -1, which means that c equals -110. All right, this is what I got on Friday. This is good news. And what's my last choice? My last choice for x? If I let x equal 1/2, then this term drops out. This term drops out, and I'm left with b times 1/2. 1/2 is plus 2 is 5/2. 5/2 times 1/2 is 5/4.
Yeah.
B equals 1/2 squared is 1/4 plus 1 minus 1 is 1/4, which means that B equals 1/5.
Yay.
So times both sides by 4, 5B equals 1. Divide both sides by 5, B equals 1/5. Now, why is that helpful? Because my final answer I can see it's going to be 1/2 ln of x minus 1/10 times 1/2 ln of 2x minus 1 plus 1/5 ln of x plus 2 plus c. However, as I see our 2 minutes, this is where I go dot, dot. I wanted to make sure we did 1 with 3. However, we'll go ahead and shorten your assignment to include, so we can do our very first original, which is easier than the last one. I'll shorten the assignment, and we'll do more integrating tomorrow. Then we're going to hold off on the new stuff. We're going to practice this again tomorrow, and I'll shorten your assignment. But for that to happen, you guys need to go ahead and take care of this closure with your partner. Be ready to share. We've got 1 minute and 15 seconds.
Thanks. Nah, it's more than
So what technique should be employed if my numerator is greater than or equal to degree?
Polynomial long division.
Polynomial long division. We have to be in f cubed. Anybody got it?
Factor.
Fully factored form. Yes. Yes. Saved by the bell. Nice job. Fully factored form was I'm going for. Awesome work today, guys.
Hooray, Matt.
Yes. Modified OTL. You guys not have it? I changed it.
Oh, yay!
Guys, I just made it 1 to 9 odd and cut off the 11, 13, and the last 3. Change that to 7.
Turn up, Terry.
I'll put